We're going to talk about fluids and electrolytes now. Yeah, so this is kind of where things can get a little nuanced. So first of all, let's just talk about fluids. And so remember we talked about yesterday how water is polar, right? Water is a polar molecule, and that enables it to undergo hydrogen bonding. And it is the fact that water is so polar and it undergoes hydrogen bonding and that it is able to interact with so many other polar molecules and ions, right, that we tend to say in biology that water is a universal solvent. So water acts as a universal solvent. And remember, solvent is just something that dissolves stuff, right? Stuff gets dissolved in a solvent. And the stuff that gets dissolved in a solvent is known as what? Solute. Good. So water, as far as we know, is critical to all biological systems, right? It is the way that we can move and shuffle things around, right? We can dissolve things in water, move them around, shuffle them around. So it is important to talk about the water in our body. So in an average healthy person, approximately, and this is going to vary from reference to reference, but approximately 60% of the weight of a person is water. Right? So not 60% of the volume, but 60% by weight. So let's just figure out how much water a generic 70 kilogram adult male patient would have. Right? So let's take a 70 kilogram patient, right? That's the generic adult male, right? What is 60%? Well, that's just 70 multiplied by 0.6. And what does that give us? You guys are going to want your calculators and your phones out for, huh? About 42, right? That gives us about 42 kilograms. So how many liters of water is that? This goes back to pharmacology. There's this really easy conversion, right? The metric system makes this conversion very easy. Huh? Right. So we said that 60% of an average adult's weight is in water, right? So 70 kilogram person multiplied by 0.6 gives us 42 kilograms. How many liters of water is that? Simple.
1 liter per kilogram.
Good,
So
right.
It's going to be
42 liters, right? In the metric system, 1 liter of water has a mass of 1 kilogram, right? So that's 42 liters of water. All right. So now what we want to do is we want to appreciate or understand where that water is distributed throughout the body. And when we look at the human body, there are how many major compartments for water to exist within the human body? What are the major compartments where I could spread this water out into?
Blood, vasculature,
Bigger picture than that.
abdominal cavity, organs.
Bigger picture than that. So you have the intracellular.
Musculature.
No. You have intracellular within the cells, right? And then you have outside of the cells, extracellular. Extracellular. These are the two major compartments that you have. Hopefully you guys learned this in anatomy. I'm sure you did, right? Intracellular and extracellular. So we talk about where is most of the water? Is most of the water inside or outside of the cells?
outside.
You'd think. It's actually mostly inside. Mostly inside of the cells. approximately 66% of all the water in your body exists within the cells, within the intracellular compartment. All right? So let's just figure that out. What is 66% of 42 liters? So 42 multiplied by 0.66, right? What does that give us?
27.
Gives us about 28, right? 27.7 liters. So 27.7 liters of that 42 exist within the cells, right? And then approximately 33% of all the water in your body exists outside of the cells, in the extracellular compartment, and that gives us approximately 14 liters, right? About 13.8 liters, right? So that gives us about 13.8 liters. Now we can further subdivide the extracellular compartment into two additional compartments, right? So what are the two major components of the extracellular fluid compartment? You guys remember? Well, where can water exist outside of the cells? That's really what I'm asking.
Here.
Your vascular compartment, right? In your bloodstream. Yeah, guys, this is not hard stuff, right? Not hard, right? So yeah, the intravascular compartment. Right? The intravascular compartment. And then where else? We have water. So we can have it in your blood vessels, we can have it within the cells, and we can have it in between the cells themselves, right? Right, you have the cells and then you have kind of the fluid in between the cells, and that's known as the interstitial compartment, right? The interstitial. The interstitial compartment. So fluid can be intracellular or extracellular. If it's extracellular, it could be either in the vascular space or the interstitial, right? Does that make sense? All right. And the interstitial compartment, about how much would you guess would exist within the interstitial compartment? Approximately 80% of all of the extracellular water is within the interstitial compartment. Approximately 80% of this. So what is 80% of 13.8? So 13.8 multiplied by 0.8. Okay, what does that give us?
Is in the interstitial?
Interstitial. So around surrounding the cells themselves.
11.
Gives us about 11 liters. Would you guys agree? So that's approximately 11 liters of water, and so that gives us approximately 20%. So most of the water in your body is not within your blood vessels, is it? A very small amount, a fairly small amount. Only 20% of the extracellular fluid, which is, again, only 33% of the total amount of fluid. So that gives us what, about 3 liters, about 2.7 liters?
So 20% is in interstitial and 80 is in intravascular.
Yes. Of this.
Of that.
Of this up here. Not this, this, right? So 80% of the extracellular fluid is interstitial. You guys didn't correct me there.
That's how it's getting nervous.
Right? And 20% is in the vascular compartment. There we go. That should eliminate any confusion there, right? So 11 of the 13 liters interstitial, and that's going to give us what, about 2.7 liters? About 2.7 liters in the vascular compartment. Okay? Does that make sense? All right. So far, so good. Cool. All right. So a very small amount of the total body water is within our vascular compartment. But here's the thing. If we are going to run tests on people to figure out what their fluid and electrolyte balance is doing, what's the easiest compartment to access? The vascular compartment. Does that make sense? So most of the lab tests that we're going to be talking about today, what we have to do is we have to sample the vascular compartment, and then we have to infer. We have to infer that based on what we see in the vascular compartment, this is likely what we're seeing occurring in some of these other compartments. Does that make sense? Right? And that inferring that we do can sometimes lead to confusion, can sometimes make it difficult to really figure out what's going on, right? Somebody, for example, somebody could have enough fluid in their vascular compartment, but be depleted in the intracellular compartment, right? Maybe they've lost fluid out of their vascular compartment, and then fluid from the intracellular has moved into the vascular compartment, right? And so they are profoundly dehydrated, even though they may have enough fluid in the vascular compartment. Those kinds of things can occur, and it can make it difficult to figure out what's going on with our patients. You guys okay with that? Okay, so that's water. And that's important because this is the solvent. This water is the solvent that's moving all of the dissolved stuff in it around, right? All the solutes, so the proteins, fatty acids, carbohydrates, right? All of the electrolytes. And remember, an electrolyte is just something that when dissolved in your blood becomes charged, right? So things like sodium, potassium, calcium, and magnesium, and phosphorus are all examples of electrolytes. Okay, so before we start talking about specific electrolytes, what I want to do is I want to talk a little bit about how we analyze electrolyte concentrations. All right? And this goes back to chemistry, and this is a concept known as a mole. This is a concept known as a mole. A mole. So we didn't talk about this yesterday, but every element, not only does it have an atomic number, and what is the atomic number? Remind me. Number of protons in the nucleus, that's the fingerprint, right? Not only does it have an atomic number, but it also has an atomic mass associated with it. Now, the periodic table that I gave you guys yesterday does not have the atomic mass, but the periodic table that you guys have from pharmacology does. So if you still have that periodic table, pull it out. And I believe is it at the bottom, underneath the symbol? Your little number underneath the symbol?
1.1.7.
There you go. Yes, that number there. That is the atomic mass. And here is a crazy thing about the elements. If I have a mole of a certain element, and a mole is just something called Avogadro's number. Avogadro's number. Okay, Avogadro's number. And it is a very large number. It is a number that's so large, it's really difficult for us to comprehend. But that number is 6.02 times 10 to the 23. Now, this is something called scientific notation. Do you guys understand what scientific notation is? Scientific notation is a shorthand way of designating very large and very small numbers. So what this means is 6.02 times 10 to the 23 is actually what? 6 followed by 23, right? I move the decimal point over. So, right, so you've got a whole lot of zeros after that. Does that make sense? Lots of zeros, right? So I move this decimal point here over 23 different places, and every time I move it over, there's a 0, 0, 0, 0, 2, all right? So does that make sense why we use this notation here, right? All right, so if I have an Avogadro's number of an element, that is also known as a mole. If I have 1 mole or 1 Avogadro's number of an element. So if I have 6.02 times 10 to the 23 atoms of hydrogen, I will have the atomic weight of that in grams. So look at hydrogen. What is the atomic weight or mass of hydrogen? It's 1 and some change. It's
.008.
1.008. So if I have a mole of hydrogen, I have 1.008 grams of hydrogen. All right? Look at sodium. If I have what's the atomic weight on sodium?
22.990.
22.9, right? So if I have 1 mole, 6.02 times 10 to the 23 sodium atoms, I have 22.9 grams of sodium. Does that make sense? What that means? You guys okay there with that? Okay. So we have to know what a mole is, what Avogadro's number is. So this is the way that it works. So electrolytes are solute, right? And when I add solute to a solvent, there are some things that happen, right? That solute interacts with the solvent, right? And that solute tends to exert what's known as osmotic pressure. We talked about that a little bit in pharmacology, right? That is that the solute tends to cause osmosis. And osmosis is the movement of water, which is solvent, right? Water from low solute concentration to high solute, right? So solute exerts a kind of pressure, if you will, that causes water to move toward it. Does that make sense? You guys okay with that? Okay. So one of the major ways in which we measure electrolyte concentrations in the body is through something called an equivalent, an EQ, an equivalent. All right? And what an equivalent is it is the moles, the number of moles that I have, okay, multiplied by the charge on those particular electrolytes, right? The number of moles multiplied by charge over liters. Because when we talk about solvent, we're talking about liters, right? We just did here earlier. Let me give you an example of how this works. Let's say that I have, and I'll draw some water here, and I have 1 liter of water. You guys okay with that? And I put 1 mole of sodium into that liter of water. And we will say sodium as an electrolyte. So when sodium is an electrolyte, what happens to it? What's an electrolyte again?
It becomes a positive charge.
Good, the sodium becomes positively charged, right? It's a cation, right? Cations and anions are the 2 major kinds of electrolytes. So sodium takes on a positive charge. So let's go to our formula. How many moles of sodium did I put in here? 1 mole. So 1 mole of sodium. And what's the charge on sodium? Positive what? How many electrons does sodium lose? Yeah, how many electrons does it lose when it becomes a cation? What group is it in?
It's
One.
one.
One, right? Because it only has one electron in its valence, so it just needs to lose one electron
Right.
to meet the octet rule. So what's the charge? It is +1, right? It's just 1. So 1 mole times 1 charge, does that make sense?
Mhm.
Divided by 1 liter equals 1 equivalent per liter. Are you guys okay with where that came from? So far so good? Okay, that's 1 equivalent per liter, all right? Let me give you another example. Let's say that I have 1 mole of calcium, and I dissolve 1 mole of calcium into 1 liter of water. Okay, so what's the number of moles of calcium do I have?
One.
1 mole of calcium. And what is the charge on calcium as an electrolyte?
2.
So this is 1 times 2 divided by 1 liter. So even though I have the same number of moles of calcium, what happened?
Equivalent changes.
Good, the concentration in equivalent changed because calcium has a +2 charge, not a +1. Does that make sense? So I would have 2 equivalent per liter of calcium. Does that make sense? You guys okay with that? Okay. So we rarely measure things in equivalents in medicine. Because if you had an actual concentration of 1 equivalent per liter of sodium in your body, that is completely incompatible with life. That's too concentrated. Does that make sense? So we have to use another unit to measure electrolytes in the body that's far less concentrated, right? So what we do is we take the concept of an equivalent and we say, well, what is 1/1000th of an equivalent? A milli, right? Going back to the metric system. 1/1000th of anything is a milli, right? A milligram is 1/1000th of a gram, right? Does that make sense? So a milli equivalent is 1/1000th of an equivalent. Does that make sense? And this is the common unit that we use to measure electrolyte concentrations in healthcare, is milli equivalents per liter. Do you guys understand where that came from? Does that make sense? You guys okay with that? Okay. Awesome. So that's electrolyte concentration. And remember, when we talk about electrolyte concentration, we always need to keep it in context with a semi-permeable membrane, right? And we got to ask ourselves, is the electrolyte concentration higher on one side than the other or lower on one side than the other, right? And then that difference in electrolyte concentration across a membrane, that difference is known as, it's a concept known as what?
Concentration gradient.
It does produce a gradient, yes. But it is a concept known as tonicity. Remember we talked about this with IV fluids in pharmacology, right? That's tonicity,
Tonic solution.
right? When I say something is hypertonic, isotonic, or hypotonic, there has to be a comparison. I'm comparing it to something else. Generally, what we are comparing is the extracellular environment to the intracellular environment. Does that make sense? Right? And the semi-permeable membrane is the cell membrane. And so if I have a very high electrolyte concentration outside of the cells, higher than outside than inside, then we would say that the extracellular environment is hypertonic compared to the intracellular environment. Does that make sense?
And that's what allows the movement of fluid.
And it is that tonicity of the solute that causes the solvent to move in or out of the cells. Does that make sense? Right? So if the extracellular environment is hypertonic compared to the intracellular environment, where is the water going to go?
Into the cell.
Into the cell?
If it's hyper outside.
If outside is hypertonic compared to inside, so there's more solute outside than inside, right?
It's gonna go extra.
The water is going to move toward the solute. Osmosis, right, is going to move. Does that make sense?
Right.
So if you have higher concentrations of solute extracellular, right, the water is going to move outside the cells.
And
Right?
it'll always move to the higher concentration.
Always move to higher concentration, right? Does that make sense?
Yeah.
This is like foundational to understanding fluid and electrolyte imbalance, because that's really what's going on is electrolyte imbalances are causing fluids and other electrolytes to shift in abnormal ways or in ways that we don't want them, right? This is like the foundation right here. If, however, the extracellular environment is hypotonic compared to the intracellular environment, that is to say the solute concentration is lower outside than inside, then what?
In the cell.
Water will move into the cell, right? So hypotonic extracellular environment tends to cause the cells to swell. Makes sense? And a hypertonic extracellular environment tends to cause the cells to shrink, or we call crenate or crenation, right? And isotonic is the concentration of solute is roughly the same outside and inside, right? So water is moving, right, there's an equilibrium, right? The water is moving in equal directions at the same time, right? There's no net movement of water one way or the other.
Now, say that again. What is that if it moves equally?
Right, so an isotonic situation is where the solute concentration is the same outside of the cells as it is inside of the cells, right? So what does that mean? That means that
It's balanced. That's what
there's
you
a
wanna
balance,
achieve,
right?
That's
Yeah.
what you-
So water is moving into the cell at the same amount that it's moving out, right? It's completely balanced.
So is that why we use isotonic solutions in EMS, because they're inherently safer when it comes to something like that?
Yes, that tends to be why we use isotonic crystalloid solutions. However, as we're going to talk about today, isotonic solutions may not be the best choice in all cases, right? Because if my problem, let's say that my problem is I need to get water into the cells, right? I have intracellular dehydration. Well, are isotonic solutions necessarily going to fix that? Not necessarily, right? I might need another kind of IV solution to cause a shift of fluid into the cells, or water into the cells, right? Does that make sense? Right? Or if I have too much, let's say I have too much water in the cells, right? Maybe I need a hypertonic solution here, right, to draw water out of the cells. So it depends, and we're going to get into that a little bit today. Okay, are you guys okay there? Now, there is also another concept that I want to talk about. Are you guys okay with moles, Avogadro's number, equivalents, and miliequivalents? Okay, what I'm going to do is I'm going to erase this now. There are some other concepts that you guys need to be aware of. So that's measuring individual electrolyte concentrations. Are you guys okay with that? So if I want to know the sodium concentration, I would measure that in milliequivalents per liter, and then I'd measure the potassium in milliequivalents per liter and other things, right? Chloride, etc. You guys okay with that? There is another concept that is closely related, but it's not quite the same thing, and it is a concept that takes the entire concentration of all the solute dissolved in water, right? It doesn't look at, well, what's the sodium and what's the potassium, right? It looks at, in general, what is the solute concentration in the body, right? And remember, when we're testing this, where are we testing it from? The vascular space. So what we're really saying is, what is the overall solute concentration in the vascular compartment? Does that make sense? And this is a concept known as osmolality. Osmolality. Let me write it down here. Osmolality. Okay? Osmolality.
That's measuring the site concentration of the vasculature.
Complete, right, total. So-
Yeah, yeah. So it's not looking at any one individual. It's like, what is the overall concentration of solute in the vascular compartment, right? And osmolality, so if I add a mole, if I have a mole of solute, now I'm not talking about a mole of sodium individually, but just a mole of solute, and I have a mole of solute dissolved in a liter, right? So a mole of solute gets dissolved in water, it's going to cause osmosis to occur, right? And so that is known as an osmole, right? An osmole is 1 mole, right, in 1 liter of water. Does that make sense? Okay, so it's very similar to equivalent. It's just looking at something a little differently. Okay, but just like equivalence, we don't deal with osmoles, we deal with milliosmol, which is actually just 1/1000th of an osmole. Does that make sense? Okay, good. All right, so osmolality is measured in milliosmoles and is milliosmoles per kilogram of solvent. So really what it's telling us is, for every kilogram of solvent I have, how much solute do I have dissolved in that? Does that make sense? That's the question that it's answering. All right. The normal osmolality in the human body is 275 to 295 milliosmoles per kilogram. MOSM, that's milliosmol per kilogram. So for every kilogram of solvent that I have in the vascular compartment, I should have between 275 and 295 milliosmoles of solute, right? Sodium, potassium, all the various kinds of solute that you have there. Does that make sense? You guys okay with that? So far, so good? So that is to say that if you have less than 275, a rule of thumb might be that the vascular compartment is going to be hypotonic. Does that make sense? Right? I have less solute dissolved in there, so the blood is going to be more on the hypotonic side. And if I have greater than 295 milliosmoles per kilogram, the blood is going to be more hypertonic than the cells. Does that make sense?
Right. And so when you're testing that,
Yes.
that's really all you can determine.
You kind of have to make some inferences. And then what we're going to do later on today is we're going to talk about history and physical. So you have a lab test, but then you got to go, okay, I see this lab here, but what's my patient's history, right? What's their chief complaint? And what's my physical exam? And what we need to do is we need to take the history and physical exam, take the lab, marry them together, and find the best picture that fits that data, right? And that's, of course, what you guys learned about differential diagnoses in the intro class and critical thinking, and did Ann kind of take you through how we think about that, right? So these labs that we're talking about today, these labs are one piece of information that you'll get, right? And you're going to have labs, and you're going to have the history, and then you're going to have the physical exam, you're going to have the vital signs, you're going to have signs and symptoms. And then what you've got to do is you've got to put that all together, and you got to go, okay, what is most consistent? What problem is most consistent with all the data that I have here? And did Ann talk to you guys about something called Occams Razor? That's something that came up, Occams Razor. So Occams Razor is a general rule of thumb that says when you are faced with multiple, so you see something and then you have a list of explanations, right? And I have multiple explanations for what I see, right?
Was it if you eliminate everything that's,
Not quite. So kind of hear me out here. So let's say that I see something, and then there are a list of three things that could explain that, right? The explanation that makes the least assumptions, right? The least assumptions tends to be the best explanation, right? For example, let's say that it is 110 degrees out and you get called for a man down. And you go and there is a 32-year-old female that was out running for an hour. She's sitting on the sidewalk, she's diaphoretic, she's sweaty, she has a little altered mental status, she's tachycardic, her blood pressure's low, she's not feeling very well. Get the picture? All right. So explanation number one is she's dehydrated. Okay, that's explanation number one. Explanation number two is a little green goblin came by and poisoned her. And she's poisoned by goblin juice. Okay, are these two potentially valid explanations for what we see? Yes, they are, right? Potentially valid. Could a goblin have come along and gave her some bad goblin juice? You don't know, right? We don't know. So yes, potentially, right? But between those, so you're faced with those two explanations, right? Which one is the one where you're going to have to make fewer assumptions? Dehydration, right? Because for the goblin hypothesis to be correct, I have to assume that this thing called a goblin actually exists, right? I have to assume that not only it exists, but it has this magical goblin juice that makes people look like they have heat exhaustion, right? I have to make lots of assumptions, right? I have to assume lots of things, whereas, oh, she has heat exhaustion. Well, that makes sense because it's hot out and she's been running and, right, everything, right? I have to make fewer assumptions there, right? Now, could we be wrong? Could we potentially be incorrect if we said that she has dehydration? We could be, right? Oh, guess what? Maybe there was really a goblin, but what are the chances? They're much lower, right? That's what Occam's Razor is when you are faced with multiple explanations for something and you're just not quite sure, you want to default to, some people will say the simplest explanation is the best, but that doesn't really catch the nuance of the fewest assumptions, right? And you guys are going to run into this a lot, right? You're gonna get called to somebody with chest pain, right? They're gonna have chest pain, history and physical exam, and you're gonna have, well, it could be this, right? It could be a pulmonary embolism, it could be an acute coronary syndrome, it could be an anxiety attack, right? You are gonna have a list of valid explanations for that patient's signs and symptoms, and you've got to make a determination as to what is your primary diagnosis, right? What do you really think might be going on? And could you be wrong? You could, right? But again, what is the simple, what is the explanation where you are making the fewest number of assumptions, right? And so Occam's Razor is a big part of this, right? These labs can be really confusing, but I just want you to remember, right? Think about what is the best explanation where I don't have to assume so much. And occasionally rare, crazy things happen, right? We call these things zebras in medicine. Occasionally a zebra can cause your patient to be sick, right? Occasionally that happens, but typically people get sick due to fairly common problems, right? Fairly common problems, right? A diabetic patient took 10 units of insulin, didn't eat breakfast, and is now unresponsive, right? Hypoglycemia is a pretty legit differential diagnosis, right? Could it be something else causing those patients? It very well could be, but hypoglycemia would be at the top of your list, right? So then what do? You check the blood sugar to rule that out. Oh, the blood sugar is 180. Okay, so now we got to think about something else. Does that make sense, right? And that's kind of the game. I'll put quotes around the game because it's serious, but that's kind of the game that we have to play as we're trying to figure out what's going on with our patients. Okay, so going back to osmolality, right? Are you guys okay with the normal range, what it is, and what it suggests? Now, there is another concept that occasionally comes up, and this concept is known as osmolality. Osmolality. Osmolality and osmolarity essentially look at the same thing. Osmolarity just looks at it slightly differently. So instead of milliosmoles per kilogram of solvent, osmolarity is milliosmoles per liter. Well, what is 1 liter of water? 1 kilogram, right? So these are remarkably similar. There's a little bit of nuance there, but they're essentially looking at the same thing. The osmolality is what we tend to use and look at in labs, and it's the concept that we will revisit here in a little bit. So are you guys okay with that? So far, so good. All right, let's get out of here, take a little break, and then we'll start talking about these labs and these electrolyte imbalances.